The concept of nuclear spin was made to explain the behavior of the nucleus in a magnetic field. If we apply a magnetic field to the nucleus will begin to align in certain directions. In the end, there will be two states of the nucleus. One is aligned in the same direction as the magnetic field, and the other one is in the opposite direction. We call low energy one alpha spin and high energy one beta spin. Beta spin has higher energy than alpha spin because of the repulsive force between the nucleus and magnetic field. In short, if we apply the magnetic field to the nucleus, energy split is occurred. We can explain this phenomenon because the nucleus has an intrinsic magnetic moment, which produces magnetic interaction with its surroundings. And we can explain this magnetic momentum arises from the spin of nucleus, which is a charged particle. But can we say nuclear spin is classically rotating? The nucleus is very similar to the Earth. Firstly, they have their own magnetic field, and we say they have spin. Earth is literally rotating. Then is the nucleus also rotating like the Earth? The answer is in quantum mechanics. As you know, all particles, including the nucleus, has both properties of particles and waves. We don't know how they actually act. Sometimes they act like particles and other times they act like waves. For this reason, we can't say that the nucleus is spinning literally. Let's go back to our nucleus spin. If we apply the magnetic field to our randomly oriented protons, they become to have certain directions and are divided into two groups. One group aligned to the same direction to the external magnetic field, and their energy state becomes more stable. The other group aligned to the opposite direction to the external magnetic field, and they becomes more unstable. Originally, there was only one energy state, but in the presence of magnetic field, we can get two energy states. As I mentioned before, this is called energy split. The energy spacing delta E becomes larger if we increase the magnetic field intensity. If we radiate the electromagnetic wave, which has energy of delta E, to the protons, the lower energy proton absorbs the energy and goes to excited state. If we apply certain frequency range of electromagnetic wave, this proton absorbs only the wave of the specific frequency, which is corresponding to the delta E. So we learned that the energy spacing is determined by applied magnetic field. But in reality, there is one more factor that determines the spacing. In chemical compounds, proton does not exist alone. It exists with other nucleus and electrons. Nucleus and electrons also have spin and act as a magnet. Therefore, the intensity of the net magnetic field that the proton feels is changed. In this diagram, net magnetic field intensity is different from the B0, which is originally applied. So the energy spacing delta E also becomes different. How can we apply these principles? Here is the application. If we synthesize a molecule, we should identify it. We can find out the chemical formula of our sample using mass spectrometer technique. Let's say it is C6H12. However, we can't find out the atomic structure just by knowing the formula because there are isomers. We can use NMR technique here. Because the electron environment of this proton and this proton are different, the energy spacing and absorption spectrum of them are also different. So we can distinguish these two compounds by comparing the absorption spectrum. From now on, we will talk about the details of this. We will see the procedure of NMR spectroscopy. This is schematic of NMR spectrometer. The sample is dissolved in a solvent and placed in a magnetic field. A radio frequency generator then irradiates the sample with a short pulse of radiation, causing resonance. When the nuclei fall back to their lower energy state, the detector measures the released energy, and a spectrum is recorded. We will see how proton NMR works to find out the structure of organic molecules. This figure is proton NMR spectrum. An NMR spectrum is a plot of the intensity of a peak against its chemical shift, measured in ppm. The formula of chemical shift in ppm is chemical shift represented in hertz, downfield from TMS, which is tetramethylsilane, divided to the frequency of NMR spectrometer in megahertz. NMR absorptions are measured relative to the position of a reference peak of tetramethylsilane at 0 ppm. Tetramethylsilane, which is CH3 or Si, is a reference molecule which is inert and has single, relatively off-field peak from typical NMR absorptions of other organic molecules. Off-field means it has a relatively low chemical shift, higher magnetic field. When we find out the structure of organic molecules, we use its four features shown in the spectra. There are number, position, intensity, and splitting of the peaks. The number of signal is same as the number of different types of hydrogen in the molecule. Type indicates the surrounding environment of hydrogen. So, for example, there is methyl third butyl ether, MTB for short, has 12 hydrogen in it. But these 3 hydrogen has same environment and these 9 hydrogen have same environment. So there is only 2 peaks for MTBE. The position of peak indicates the types of hydrogen. We have seen that if electron surrounds proton, magnetic field induced by the electron suits the external magnetic field. Since the nucleus experiences a lower magnetic field, it needs a lower frequency to achieve resonance. Lower frequency is right side in an NMR spectrum toward a lower chemical shift, so shielding effect shifts the absorption of field. In summary, higher electron density means upfield, and decreased electron density means downfield. The peak of proton in a certain environment is in a predictable region in an NMR spectrum. For example, if a peak is appeared in this region, we can predict this proton is independent ring. Like this, we can find out environment of proton by the position of peak. Intensity of the peak indicates the relative amount of each kind of hydrogen in the molecule. The area under a proton NMR signal is proportional to the number of absorbing protons. A NMR spectrometer can integrate the area under the peaks, and modern spectrometers can even automatically calculate and plot the value of each integral in arbitrary units. The ratio of integrals means the ratio of absorbing protons in a spectrum. Be careful that this only gives a ratio, not the absolute number of protons. You can see the MTB spectra here. There are 12 hydrogen in MTB, but the number given is 20 and 60. It only shows that this peak has 3 times of the number of protons in this peak. So we have to calculate to find out the actual number of protons in each peak. Because MTB has 12 hydrogen, this peak is the absorption of 3 hydrogen, and this peak is the absorption of 9 hydrogen. If the signals for protons are split into more than one peak like this, spin-spin splitting occurs only between non-equivalent protons on the same carbon or adjacent carbons. Splitting gives further information of the neighboring environment. For the various hydrogens in the molecule. Let me explain the principle with some examples. How does the doublet due to the CH2 group on 112-tribromoethane occur? When placed in an applied magnetic field, the adjacent proton can be aligned with or against it. Thus, the absorbing CH2 protons feel two slightly different magnetic fields, one slightly larger than B0 and one slightly smaller than B0. They absorb at two different frequencies in the NMR spectrum, thus splitting a single absorption into a doublet. Then what about triplet? Because there are two different ways to align one proton with B0 and one proton against B0, the middle peak of the triplet is twice as intense as the two outer peaks, making the ratio of the areas under the three peaks 1 to 2 to 1. If there is a set of n non-equivalent protons, then it splits the signal of a nearby proton into n plus 1 peaks, if n is bigger than 2. So, with those four features of proton NMR, number, position, intensity, and splitting of peaks, we can find out the connectivity of elements, which leads to the structures of molecules. I hope you can easily find out the structure using NMR spectroscopy.